Welcome back, everybody. Today we're going to make a big shift in our emphasis. We've been studying all semester long what's been called supervised learning. In supervised learning, you're given data with labels, and then you want to try to predict the labels of other data points that don't come with them. Unsupervised learning is the question of what do you do if someone gives you sample points but no labels? So in other words, there's no classes, there's no y values to estimate or interpolate or regress. There's nothing really to predict. So what can we do besides prediction? Generally, the goal of unsupervised learning is to just discover structure in the data. And I'll give you a few examples. The three most well-known forms of unsupervised learning are called clustering, dimensionality reduction, and density estimation. Clustering is when you want to take your data and partition it into groups. Typically, the groups are each made up of similar data points. Or, to put it another way, points that are close to each other. And we'll talk about clustering on Wednesday. A second kind of unsupervised learning is called dimensionality reduction. The idea behind dimensionality reduction is to notice, first of all, that in many applications, you find that your data often lies near a low-dimensional subspace of your feature space. And so subspace or manifold, a manifold is kind of like a subspace except it's curvy. It curves in your feature space. And so the idea here is that maybe the data you have is not really using all the dimensions available to it in some sense. And you can kind of flatten it out and look at it in a lower dimension and get a sense of what's close to what and how things vary across space. Another example of that comes up in matrices. Matrices have a low rank, I should say, low rank approximations. So, whereas clustering is about grouping similar points together, dimensionality reduction is more like identifying a continuous variation across your data points. And very soon I will spend the rest of the lecture on the most famous example of dimensionality reduction, which is called principal components analysis. The third example of unsupervised learning that comes up a lot in statistics is called density estimation. And here the goal is to fit a continuous distribution, a probability distribution, to discrete data. Now, we've already studied an example of density estimation in this course when we learned maximum likelihood estimation is kind of the premier technique for density estimation. But there are lots of other techniques because in particular, what often happens with more complex data sets is that you can't maybe fit your data with one Gaussian, but maybe you can fit your data with several overlapping Gaussians. And so things start to get interesting when your distribution is not just a simple Gaussian, but some combination of Gaussians or maybe some even more complex distribution. So those are the three most famous kinds of unsupervised learning. And I will spend the rest of today talking about, the most famous one of all. Principal components analysis is a lot of syllables, so it's almost always called PCA for short. It's an old algorithm. It was invented by Carl Pearson in 1901, at literally the turn of the last century. So the idea is someone gives you a bunch of sample points in d-dimensional space. And what we're going to do is we're going to try, we don't necessarily want to have d dimensions. Maybe d is too many. Maybe we just want to try to get by with k dimensions. So let's find the k directions in our d-dimensional space that carry most of the information. Or a little more precisely, that capture most of the variance, or I'll call it the variation between the different points. And again, PCA is an example of dimensionality reduction. And an illustration, I think, goes a long way to showing you exactly what this means. So here is a very simple example where we take a 3D point set on the left and reduce it to a 2D point set on the right. So d equals 3, k equals 2 in this example. And looking at those points on the left, what we've done is we've chosen a plane through the origin. And having chosen that plane, we project all the points orthogonally onto that plane. So you can see those little projection lines. They're all perpendicular to the plane that we're projecting onto. And so those points get projected down from 3 dimensions to 2 dimensions. And what we're left with is the points on the right. And the question is, how do I do this? How do I choose that plane so that I don't lose more information than necessary? Hopefully I still have most of the understanding I had before of how these points vary, how they differ from each other. So projecting from 3D down to 2D is the best way to give us intuition for what's going on. But what's very commonly done in practice is that we project down from a much higher dimensional space. And so here is an example where we are projecting down the digits that from the MNIST data set that you worked with, for instance, in homework 1. And so what we're doing is we have points in a 784 dimensional space because they're little 28 by 28 bitmaps. So that's a 784 dimensional space. And there are 10 different colors here. If you look at the upper right-hand corner, you'll see there's a little key here, and it says that the red dots represent examples of the digit 0, handwritten zeros in our database, like these ones here. And orange is the ones, like these ones here. Yellow is the 2s, and so forth. So what happens if you take that 784 dimensional space and you project it down to just 2 dimensions? We have lost a fair amount of information here. Like, if you try to classify the points using only those 2 dimensions, you don't really have enough information to tell the digits apart successfully. But if we were to project down to a 4D dimensional space, you probably could still reliably tell the digits apart. I can't show you what the points look like in 4D dimensional space, though. But even in this example, you can see some digits are pretty easy to separate. Specifically, let's look at the zeros and the ones. Remember that the zeros are the red points, and you can see that most of the zeros have projected to this part of the image. The ones are the orange points, and you can see that most of the ones have projected over here. So it looks to me like even in two-dimensional space, you still retain enough information to distinguish zeros from ones, which is impressive. If you want to distinguish all 10 digits, though, maybe you need 20 dimensions. Maybe you need 40. This kind of plot is very, very popular, especially in biology journals. I'll show you an example later. There's all kinds of things in biology where people like to do little PCA plots of genetic data or other biological data to try to get a sense of how things are spread out, what's variations among species or other biological properties. So next thing I want to address is, why do we want to do this? What will this give us? There's a number of reasons why this could be useful. One is sometimes it's just a good idea to reduce the number of dimensions before you do some other computation like regression. Because doing computations on lower dimensional points is just plain faster. So you know, if I have points in 800 dimensional space and I reduce them to 40 dimensions, I've reduced their length by a factor of 20, and maybe my code for regression will run 20 times faster. That's pretty good. Along the way, you might find another advantage that is related to subset selection. Remember that if we have features that are not predictive, throwing them away often gives us better generalization to new examples, better test error. PCA gives you another way to remove irrelevant dimensions or irrelevant information. It's just now their dimensions you're removing are not necessarily features per se, they're linear combinations of features. As a result of removing some dimension, you might actually find that you get less overfitting. If you have fewer parameters to fit, then you have less chance of overfitting with regression or classification algorithms. So again, this is very much like subset selection. We're basically taking the feature space and we're reducing its dimension, which is what we do in subset selection too, but we're doing it in a more complicated way. There's a sense in which the features that we're keeping and the features that we're throwing away are not axis aligned, by which I mean they're not actually the original features, they are linear combinations of the input features. Another use of PCA is to find a small basis for representing variations in complex things. You want to know, you might want to ask yourself the question, what are the most significant ways in which one person's face varies from another? And so PCA can actually tell you a lot about that. And I suppose the most use of PCA of all is just visualization. Like I said, if you comb through journals on biology, you just find thousands of PCA plots. The first two things on this list in particular are often reasons why PCA is used as a pre-process for some other learning algorithm like classification or regression. Before I dive into the algorithm, are there any questions about what I've said so far? Yeah.
You mentioned that like there are linear combinations of input features.
Mm-hmm.
Maybe when we do PCA, we lose like some interpretability.
Yes, that's a good question. Yeah, when you do PCA, absolutely you lose some interpretability because now instead of telling the world this stuff depends on these features, it's now, well, our first principal component is 0.33 times feature 1 plus 0.08 times feature 2 plus blah, blah, blah. So yeah, you definitely lose interpretability. That is true. All right, our input is going to be a design matrix. And that's all. There's no labels as input. Also, you don't need a fictitious dimension. So remember, when we do regression, when we do perceptrons, we used a fictitious dimension. You don't need that here. All right, so the first thing we're going to do is center that matrix. And I don't want to change notation, so let's just assume that X has already been centered. So I can use the notation X for the rest of the lecture, which means if you take the average of all the sample points, all the rows of X, that's 0. Mean value of a sample point, that is, the mean over all sample points xi is 0. Of course, in practice, you're not usually given a centered matrix. You're just given a design matrix, and the first thing you do is center it. You compute the mean of all the sample points. You subtract the mean from every sample point. Now you have a matrix that's centered. So that's what we'll assume for the rest of this lecture. All right, to think about what the math is going to look like when we use principal components, let's suppose we've already found one of the directions that we think is important. One of the directions that captures a lot of the variance in our data set. And we're going to call that a principal direction or a principal component. And I'm going to call it W. I haven't told you how to find W yet, but let's suppose we've already found it. I'm going to assume that it's a unit vector. I like my principal components to be unit vectors because that simplifies things. And given that, now I might want to compute the orthogonal projection of some sample point, let's call it little x, onto this principal component vector W. Now, here is the formula for that projection. So I'm using x with a little tilde on top of it to mean the projection of data point x onto the subspace that I've chosen for PCA. And this x dot w, well, you can think of that as the how far you have to go in the direction w. So let's suppose that this is the origin of your coordinate system, and w is a unit vector pointing in this direction. And you have a data point x, and you want to project it onto the subspace spanned by W, which is this line here. So the orthogonal projection means that I'm going to drop an orthogonal line down, or an orthogonal line segment down to that blue dashed line, and whatever point it hits, that's my projection x with a tilde. So coming back to this formula over here, x dot w, this dot product here, that's essentially the distance from the origin to x tilde. So it's telling you how far you have to go in the direction w to arrive at the projection. So that's what that formula means. So at this point, we're just looking at one principal component. The idea is that we're going to pick the best direction w. The direction w such that when I project down all the points, I lose as little information as possible. I maximize the variance of the projected points on that line. Of course, when I project down some high-dimensional data set to just one dimension, I'm losing a lot of information no matter how good that line is in all likelihood. So typically we want to project down to more than one direction. So pick several directions. Those directions span a subspace. We want a way to project x down onto that subspace. This is easy to do if the vectors you have spanning that subspace are orthonormal. So they're all perpendicular to each other. They're all unit vectors. In that case, it's really easy to generalize this projection formula to a multidimensional subspace. For that to work, I'm going to assume that somebody gives me some nice directions. Let's call them v1 through vk. And again, this word orthonormal means they're all mutually orthogonal. They're all perpendicular to each other, and they all have length 1. So given that, my projection formula is basically the same. It's just that now I have to sum over all of these. So each principal component will make a contribution to our projected point along some direction, and those directions are orthogonal to each other, so we can compute these independently. And the tuition for this is you should imagine that there is some plane, for instance. Let's suppose we've got two principal directions. Then they span some plane. And I'm going to draw my plane by drawing a square in that plane. I know that looks like a parallelogram, not a square, but that's because we're looking at a square from an oblique angle. So imagine this is a square in 3D space. We're looking at it from an oblique angle, which is why it doesn't look square. But the origin is here, and the two vectors that we're using are v1 here and v2 here. And yes, they are at right angles to each other, even though it doesn't quite look like it, because we're looking at it obliquely. And so now we have a point x. And again, we want to project it orthogonally onto this subspace. So again, this needs to be a right angle. And that's going to give us our projected point x tilde. So what this formula up here is saying is that I can treat each of the principal directions independently. So I can project x onto the vector v1, and that gives me a point. I can project x onto the vector v2. That gives me another point. And those 2 points essentially, I can think of them as independent coordinates in a two-dimensional coordinate system that lives on that plane. And so again, let me emphasize that the length of this portion here, the length of that is x dot v1, and the length of this portion here is x dot v2. So that's this part of the formula. And so we think of the x dot vi as being coordinates in some special coordinate system that lives inside our subspace. And sometimes we don't actually want the projected point. Sometimes we do. It depends on your application. You may want the projected point in the full d-dimensional space, but very often all we want is these coordinates here. Very often all we want is the coordinates in the low-dimensional subspace. That way we have a lot less coordinates to deal with. So again, these x dot vi's, they're called the principal coordinates. So principal coordinate, that's this part here. And the vi's themselves, those are the principal components. So that's the difference between the principal coordinates and the principal components. Any questions about any of this so far? All right. So now that we've got this, I want to talk about how we get some good principal components. How do we get the directions that define our subspace? We get them from the matrix X transpose X. So remember, X is the design matrix. When we compute X transpose X, we get a matrix that is square and symmetric. And hopefully you all remember from homework 2 why it's positive semi-definite. And since X is an n by matrix, X transpose X is a d by d matrix. And as it's a symmetric matrix, its eigenvalues are all real valued. No complex eigenvalue. So let's write the eigenvalues in sorted order. I'm going to use the convention of using just the smallest index for the smallest eigenvalue. So lambda 1 is the smallest, and lambda d is the largest eigenvalue of X transpose X. As it's a positive semi-definite matrix, there are no negative eigenvalues here. With that notation, let's write down the corresponding unit eigenvectors that go with those eigenvalues. Emphasis on, we really want the unit eigenvectors here. It just makes all these projections and computations a lot easier. So these eigenvectors are called the principal components. And they're orthogonal to each other because the eigenvectors of a symmetric matrix are orthogonal to each other. And they're unit vectors because we make them unit eigenvectors. We scale them. And the most important principal components will always be the ones with the biggest eigenvalues. So the eigenvalues kind of tell you how much information is carried in each principal component. Big eigenvalue means more information. So, what I just said was a claim. The most important principal components will be the ones with the greatest eigenvalues. So I want to show you that now. And I want to show you that in 3 different ways. So I'm kind of going to give 3 different motivating derivations for principal components analysis. First one, we're going to bootstrap from something we already know. Remember when we learned how to use maximum likelihood estimation to fit a Gaussian to our data points? Well, what did we do? We centered our data matrix. We took X transpose X, where X is the centered data matrix. We divided it by n, although the constant doesn't really matter. And that gave us our sample covariance matrix. Then we did an eigendecomposition of the sample covariance matrix to understand how our Gaussians' axes were aligned. And so, since we already know all of that, we can just do that and choose the k Gaussian axes have the greatest variance. So, here's a figure that conveys some of the sense of what we're doing here. So in this figure, you've got your data, which is the red x's, and we fit a Gaussian to those red x's, just as we learned to do some weeks back, a month or 2 ago. And so once you've got that Gaussian, you've got its isocontours here, and we know, you'll recall, that the way you get this is by taking the eigendecomposition of X transpose X, and then the largest eigenvalue of X transpose X is going to tell you this is your first choice of principal components. This is the first principal component you want to project your data onto, because clearly it expresses more of the variance in this among your data set than the other component does. The other component expresses less variance. So V2 will be our first choice. Is our second choice here. We can project this data down to 1 dimension. We project it onto V2. So for now, that's the most intuitive answer, but my other 2 derivations coming up will be more mathematical. So again, presuming X is centered, this is our covariance matrix. When we fit a Gaussian, that's our covariance. So before I go on to the other 2 derivations, I want to actually write out the algorithm now. here is the PCA algorithm. First step, center X. Next step, this is an optional step, but you might want to normalize your data. Now, the rules of thumb for whether you should normalize or not are the same as they have been for other things we've studied earlier in the semester, like SVMs. The most important consideration is, do you have features that are in different units of measurement? So one of the things about PCA is that the scale of the different features really matters for the result that you're going to get. So if you have one feature that's measured in seconds and another feature that's measured in meters, they're not really compatible with each other. So it makes a lot of sense to normalize them. Because it's just bad for principal components to depend on some arbitrary choice of units of measurement. You know, if you use centimeters instead of meters, you get a totally different answer. But there are many circumstances where every feature represents the same unit of measurement, the same kind of scale, especially, for instance, genetic data is a very common example of that, where each feature is just a 0 or a 1. And in that case, you usually do not normalize the data. But again, you have to understand your application ultimately before you make this decision. The next step, whether you normalize or not, is now we're going to compute all of the unit eigenvectors and corresponding eigenvalues of X transpose X. And then you need to decide how many principal components do I want to use? What should my value k be? And sometimes that's an obvious choice. If you want to do a little plot on paper in your science journal, usually you pick k equals 2 because paper is two-dimensional. But often there are better reasons to pick other k's. And one optional thing you can do is not predetermine it, but sometimes what you do is you actually look at the sizes of the eigenvalues, compare them to each other, and use that to decide how many of the eigenvectors you need to use as your principal components. But whatever k you pick, whatever dimension of subspace you pick, the next question is, what is the best k-dimensional subspace? Meaning, when I project my data down to a k-dimensional subspace, how do I maximize the amount of information that I retain? And the answer there is you pick the eigenvectors associated with the k largest eigenvalues, which are the eigenvectors starting from v subscript d minus k plus 1 up to vd, which is the best one. Then the next step is computing the principal coordinates. Of the form x dot vi. What is x here? Well, could be a training point, could be a test point, depending on what you're going to use your subspace for. Technical detail, when you project your data down onto the subspace you've chosen, you have two choices. You can project the original uncentered training data, or you can project the centered training data, in which case your projected data will still be centered. If you do the latter, you have to remember to translate the test data by the same vector that you used to translate the training data when you originally centered it. So after you've computed the principal coordinates, you can optionally compute the projected points in the high-dimensional, d-dimensional space as well. But as I said, more often than not, we don't need those. Very often, we just want the principal coordinates. Any questions about that? Yeah. So how does training and test data differ? For instance, suppose that you're using PCA as a pre-process for regression. So the regression algorithm is going to have training points and test points. So when you do PCA, you'll be doing PCA on the training points, and then you'll feed those lower dimensional principal coordinates into the regression algorithm, do regression on those. But later on, you're going to want to use that algorithm to regress values on test points. And when you do that, you still have to run those test points through PCA before you can plug them into the regression algorithm. So in that case, it's important that you translate them by the same amount you translated the training points before you plug them into the regression algorithm. Make sense? All right. Yes? Yes. Once you have computed principal components from the training points, we're never going to change them. It doesn't matter what the test data is. Yeah? You're not going to do PCA again on the test data. You're going to compute principal components from the training data only. Once you've computed those, you're never going to change them. When you get test data, you have to project that test data onto the same components, but you're not computing any new components, no way. Yes? Does normalizing ever hurt our accuracy? Of course. If you may well want to use validation. Like suppose you're using PCA as a pre-process for regression. In that case, you may not know in advance whether normalizing will give you better or worse regression results. Validation is the best way to find out. Yeah. Why don't we run PCA on test points? Well, it's too... You're not necessarily given the test points when you're given the training points. It's very common where you need to build a model in advance, and then someone's going to throw a test point at you and say, quick, classify this. That's a very common mode of operation. Once you've trained something, then you're using it continuously all day long with test data coming in from your engine users or whatever. Now, one thing that one of your textbooks has is this figure that compares normalizing with not normalizing. And the main bit of information that you're supposed to take from this is it is not always clear whether you should normalize or not. What's going on here is that someone has four-dimensional data. And the four features in that four-dimensional data are, well, we've got a bunch of cities, so each training point is one city. And for each of those cities, we have the urban population, and we have the annual rates of rape, assault, and murder. And so the question is, should you normalize those four numbers before you do PCA or not? You get very different results if you do or don't. So the one on the left is normalized. The one on the right is unnormalized. To understand the axes, remember there's a four-dimensional coordinate system here. So imagine the unit vector for each of the 4 coordinates. Suppose we take those unit vectors and we project them down onto our 2-dimensional subspace, then that's going to give us these arrows here. So this gives you a sense of how much each of the original 4 features contributes to these projected 2-dimensional features. And the thing that you'll notice is that on the left, they all have a pretty strong contribution. On the right, the rape arrow is pretty short, and the murder arrow is really, really short. And the reason for that is there aren't nearly as many rapes as there are assaults, fortunately. And there aren't nearly as many murders as there are rapes, fortunately. So because there's just not very many of those things, when you don't normalize, they don't have a big effect on the PCA. And so you might ask, well, which one of these is better? Well, neither of them is better, but for a particular application, one of them might be better. If you are interested in just giving the populace a general idea of how bad crime is, well, the one on the left is probably more appropriate because there aren't very many murders, but people are more concerned about being murdered than they are about being assaulted, so it makes sense to, as a gauge of actual danger. On the other hand, if you want to know how your police officers are going to be spending most of their time, maybe the one on the right is better because obviously if there are more assaults, then assaults are going to be a bigger contributor to police time than murders are. So again, the main point, though, is that there are situations where it's very ambiguous whether you should normalize or not. Yeah?
Are there different colors of data points to signify different types of crimes, or does each data point have like 4 features?
The latter. Each data point has 4 features, and 3 are just counts of how many crimes happen per year.
I think I'm still confused as to how normalizing changes this, and then also how if we have a small amount of data points for a certain feature, and that would consider them like overlapping things. Has this really affected?
Oh, well, I mean, there isn't a correspondence between data points and features here. We're not doing classification. There aren't rape data points and murder data points. They're just cities, different city data points. So the main effect that normalization has is it takes numbers that are very small and makes them bigger. It takes numbers that are really big and makes them smaller. So it kind of assumes that all of the axes deserve equal consideration. But the actual count of things that have big counts are just going, if you don't normalize, things that have big counts are going to have a much bigger influence on PCA than things that have small counts. Mm-hmm. No, when you normalize the data, it does not mean that all the singular values are 1. So the question is, why is it in the first figure, why don't those 4 arrows all have exactly the same length? Let's consider the following data set. So this data is definitely not isotropic, but it is normalized because in the x direction, the variance is the same as in the y direction. So variance in this direction is the same as the variance in that direction. So when you normalize the data, this won't change. But when you do PCA, well, you've got one direction that's very strong and one direction that's much weaker. Because PCA is allowed to rotate and normalization is not. The other thing I wanted to talk about briefly is how you might choose the number of principal components dynamically. And so here's a drawing someone did where they took some data in 17-dimensional feature space. They did PCA, and they plot how much variance, in a sense, does each of the 17 principal components have. And the formula for that, what's being plotted on the y-axis here, is the percentage of variability is defined to be the sum over the first k, or sorry, not the first, the biggest k eigenvalues divided by the sum over all of 17 eigenvalues. And so that'll be monotonically increasing with k. So you'll notice that according to the graph, when you have just one eigenvector, you've already captured 40% of the variability. When you have 3, you've already captured over 70% of the variability. So in this example, 3 might be good enough. You could argue that. Having said that, though, if you are using PCA as a pre-process for a supervised learning algorithm, there's a better way to check k, which is validation. So try different values of k and see which one gives you the best generalization, the lowest test error. Now I want to give you a second derivation of PCA. I told you that we're looking for the subspace that will maximize the variance of the data, in a sense. And here I want to show you that's literally true. So you can think of PCA as looking for the direction that maximizes the sample variance of the projected data. In other words, when we project the data down, we don't want it to all bunch up. We want it to be as spread out as possible. So, little figure to get the idea across. Here is the black circles filled with white, for the most part, are data in two-dimensional space we want to project. So we choose a green line, and we project all the points onto that line. And we want to choose the green line through the origin that maximizes the variance of the positions along that line. So let me write this as a formal optimization problem. So at the moment, we're looking for just one vector. We want the best vector, the best principal component. And so to find that, what we want is, well, let's look at all of our projected training points. And let's just look at their principal components. Since we're projecting onto one vector, the principal coordinates are just going to be like, there's just one principal coordinate for each data point. So you can think of them as real numbers, real number line. And let's compute the variance of those real numbers. And so that is the formula for variance. Oh. one thing I should explain here is that for the purposes of this optimization problem, I'm not going to assume that W is a unit vector. So I am dividing by the length of W here because I want to make this be a unit vector. But so given that the data is already centered, and when you project it, it's still centered, this is the formula for the variance of those principal coordinates. So that's just the standard variance formula from your statistics class when the mean is 0. And we can simplify this a little bit. By putting it in a matrix representation. So get rid of the summation, replace it by a matrix vector multiply x times W. And it is sometimes really hard to write that out in a slightly different form. I'm going to actually, and of course, the reason why I wrote this out is when you do this, it exposes our matrix that we're taking the eigenvalues and eigenvectors of. You can see that it actually appears in our objective function. Now, this expression is one that comes up often in different areas of mathematics, and it comes up often enough that it has a name. It's called the Rayleigh quotient. In this case, it is the Rayleigh quotient of the matrix x transpose x and the vector W. And when you see a Rayleigh quotient, you should smell eigenvectors nearby. You're getting really close to eigenvectors. So, all right, we want to maximize this thing. How do we maximize it? First of all, let's just consider a special case. Suppose W happens to be an eigenvector of x transpose x. Let's say eigenvector number I. In that special case, what is the Rayleigh quotient? Well, when we compute x times vi, we get lambda I times vi. So no, I'm sorry, that's wrong. When we compute x transpose x times W, where W is equal to Vi, then we get lambda I times Vi. Therefore, when you plug an eigenvector of x transpose x into the Rayleigh quotient, the Rayleigh quotient itself has a value of lambda I. So what this tells us is that if we restrict W to be one of the eigenvectors, and you want to maximize the Rayleigh quotient, then of course you choose VD, because VD has the biggest eigenvalue. And so that will achieve the maximum possible variance, which is lambda D over n. Okay, but what if W is not restricted to be an eigenvector? What if W could be any vector? Well, I don't have time to prove that, but no other vector can beat VD. And this is not a difficult proof. I just don't have time to go through it. But if you want to see the proof of that, look up Rayleigh quotient in Wikipedia. It is there. The short intuition is that because every vector W is a linear of the eigenvectors, then when you plug in any W, you're always going to get a number between lambda 1 and lambda d. You can never go over lambda d. All right, so anyway, what this proves is that the eigenvector associated with the largest eigenvalue gives us the best principal component, the one that maximizes the variance of the projected points. But we typically want k different directions. So after we've picked one direction, now we want to pick a second direction that is orthogonal to the first direction. But subject to that constraint, subject to the constraint that the second vector we choose has to be orthogonal to the first vector we chose, we again want to minimize that formula for the variance of the points projected onto the second vector. And it turns out that the optimum value then is going to be the eigenvector, Vd minus 1, associated with the second largest eigenvalue. And if you need a third direction that's orthogonal to both Vd and Vd minus 1, Vd minus 2 is optimal. And so on. And it is possible to show that the combination of those eigenvectors gives you a subspace that is the optimal solution to the question, what is the best k-dimensional subspace? Any questions about that? All right, on to derivation number 3 of principal components analysis. And here I want to show you another thing that is optimized by PCA. Suppose, forget about the variance, I ask you to find the direction W that minimizes the mean squared distance that the point moves when you project it. Let me visualize this so you can see what I mean by mean squared projection distance. So in this animation, we have a bunch of data points in blue. We are taking our line and we're rotating it around the origin, trying to find the best line. And what I want you to notice is the red edges that connect each data point to its projection on the line. So what we want to minimize is the sum of the squares of the lengths of those red edges. So again, we want those red edges to be short. And you can see as we rotate, we're getting shorter, we're getting shorter, we're getting shorter. That's the optimum. Now you can see the red edges tend to be getting longer and longer and longer. And that's the reverse optimum when the max of the sum of squares of the red edge lengths. And bang, that's the solution. So you can think of this as being a sort of least squares linear regression. But there's one subtle and very important change. When you do standard least squares regression, you have a special direction, the label direction, the y direction, and we are trying to minimize the sum of the squares of the errors in the y direction. When we do PCA, you don't have a special direction anymore. It's just the direction orthogonal to the subspace that you choose. So here's a couple of illustrations that show you that difference. On the left is least squares linear regression. On the right is PCA. Now, on the left-hand side, there is a special direction, the y direction, and we are trying to minimize the sum of the squares of the lengths of these error bars that pass in the y direction, the direction of the label. On the right-hand side, when we do PCA, there is no special label direction. All the different features are treated equally. So instead, we look at the distance from each point to the subspace itself in d-dimensional feature space. And we try to minimize the sum of the squares of those lengths. And that's pretty much the only difference between least squares and PCA, except that they lead to very different algorithms. PCA needs eigenvalues and eigenvectors, and least squares does not. So with that subtle change in mind, now let's think about what we're trying to optimize. Again, let's write it as a formal optimization problem. We are now looking for, let's start with just one principal component. We want the principal component W that minimizes the sum of the squares of the projection distances. So by projection distance, I mean for sample point I look at xi minus x tilde I, x tilde I being the projection point. And well, what is x tilde I? It is xi dot w over length of w. Again, I'm not going to assume w is a unit vector. Times w, so I have to divide by w length again. So that's what I want to minimize. Well, to minimize this, you need to expand the square. And when you expand that square, you get 3 terms. And it turns out that the last 2 terms will partly cancel each other out. So you wind up having only 2 terms after all. I recommend you actually try working this out after class so you see how we get to what I just wrote, to what I'm writing now. It's not obvious at all. But I promise you that the thing above is equal to the thing below. And what's interesting about that version is the sum over all the xi squares, that's a constant. That has nothing to do with w, so we can drop that. The only part that's actually going to matter is the sum of this stuff here, and that is what we optimized in PCA derivation number 2. So this thing here, that's the variance. So just to make that clear, this is going to be, the first term gives us a constant, which isn't going to affect the optimal w. And the second term is just n times the variance that we computed in derivation 2, and that we already proved was a maximizer. Well, now we want a minimizer, but remember there's a minus sign, so this optimization problem is optimized by exactly the same result as the previous optimization problem from derivation 2. So that is our formal optimization problem. And this means that minimizing the mean squared projection distance is equivalent to maximizing the variance. And so from this point on, we can just carry on with the same reasoning as in derivation 2 and get the same result, the same conclusions. Any questions about that? Yeah. How you constrain to already chosen principal components, like when you're doing this for the second, trying to find the second? Say that again? Yeah. I mean, one way to think about it is remember the first interpretation. Remember how I talked about we're fitting a Gaussian to the data. That's what this algorithm is doing implicitly. Fit a Gaussian to the data, and then just look at the axes of the ellipsoidal isocontours of that function. And so one thing that naturally comes about from symmetric matrices is that the axes are going to be orthogonal to each other. So you kind of get that naturally for free. And so therefore, I can just, when I solve the first problem, discover that V2 is the optimal choice. So that's my first choice. And then when I'm done that, now I want to solve the problem of optimize either function 2 or function 3, like function from derivation 2 or function from derivation 3. Doesn't matter which one I'm optimizing. Either way, the goal is find a direction that is orthogonal to the first direction that either maximizes the variance or minimizes the sum of squared projection distances. Either way, this is going to be the answer because of the happy accident that symmetric matrices always have orthogonal eigenvectors. Yeah, that's right. Yeah, you're projecting down to an eigenspace and you're solving in that eigenspace, but you can prove that that's very easy. Yeah. If x transpose x is singular, then some of the principal coordinates are going to be zeros. That's fine. Although it does mean that this particular interpretation is now a little, trickier because you don't get ellipsoids anymore, you get cylinders, but it still works. Yeah. To choose non-zero features. The difference between this and other methods of subset selection is that methods of subset selection like lasso or just simple subset selection are eliminating specific input features. That is very good for interpretability because it tells you which of your data you don't need. It tells you which data you don't have to gather anymore. It tells you scientifically the model depends on this thing, but it doesn't depend on that thing. So PCA does not give you something that's interpretable. It does not relieve you of collecting any data. Where it does have an advantage is when you know that your data has maybe rotated in space, and so that spatial representation needs to be chunked down. And one example where it needs to be chunked down is genetics. I've been telling you repeatedly that biology papers often use PCA for visualization. So what I want to show you now is one of the most startling examples of that I've ever seen. This is from a paper that appeared in Current Biology. That's the name of a journal, Current Biology, in 2008. And what they did was they had a design matrix that represented the genes of 2,541 people in Europe. And the features for each of these 2,500 people were what are called SNPs, that's short for single nucleotide polymorphisms, which are essentially binary values, 0 or 1, that together convey a lot of information about what's in your genes, what's in your genetics, that is. And so the number of features per person was 309,790. So this is a huge number of genes, almost a third of 1,000,000 genes for each person in this matrix. Again, 2,500 people from a variety of different countries, including, here is UK, Spain, Portugal, France, Switzerland, Netherlands, Norway, Denmark, Sweden, Finland, Poland. DE is Germany, Italy, Austria, Hungary, etc. So they took people from all these different countries, and they took their SNPs, their genetic data, and they projected this 300,000 dimensional space down to 2 little puny dimensions. And what they got is here on the left. They didn't actually plot all 2,500 points, because that would just maybe not be very clear. What they did is they plotted outlines of the regions that say lots of people from this country mapped to this region. So when you do PCA on the genes, what you find is that most of the people from the UK kind of fall in here, most of the people from Denmark around here, Norway here, Sweden here, Germany here, and so on. And what's really startling about this is that the genetic map looks a lot like the geography of Europe. Like, the distance between your genes and some other Europeans' genes literally depend more or less on how far apart you live in miles, which is crazy. It's almost too good to be true. So that's kind of one example of you will find biology papers are full of these PCAs of genes, of SNPs, all over the place. But this is one of the most crazy, amazing examples I have seen. So in my last 2 minutes or so, I just briefly want to talk about eigenfaces. What this is a demonstration of the fact that PCA can give you a sense of what are the most important ways in which human faces vary from each other. And in this case, our design matrix contains n images of faces with d pixels each. And since I'm short on time, I think I'll stop writing, but I will tell you that if you have a 200 by 200 face represented as a 40,000 dimensional vector, just like we do the MNIST image data, suppose you want to do face recognition. Given a query face, compare it to all the training faces. Well, since each face has 40,000 pixels, comparing 2 faces takes big O of 40,000 time. Can we reduce that by using PCA? Quite a bit. So if you can reduce the size of your image from 40,000 to, say, 400 principal coordinates, you speed up your code by about 100, right? So people have tried this, and I will show you what principal components look like when you apply it to faces. So first of all, the first thing we do, remember, is we center our design matrix. So upper left, this image here, that is the mean of all the faces. So you subtract the mean face from all of the individual faces in your design matrix. You do PCA. And then they showed the top 119 principal components. And the most important principal component looks like this. This is the number one way by which different people's faces vary when you reduce them to 2D pixels anyway. At the other extreme, you'll notice that by the time you get to the 119th eigenvector, it looks pretty much like noise. That's not a very useful principal component for distinguishing different people's faces. And then here are the rest of the principal components. I want to mention that sometimes the first few components depend more on lighting than on the actual shape of your face. It depends exactly on what your data set looks like, what conditions it was taken under, but sometimes people discard the first few because they want to factor out lighting and just look at differences in people's actual face shapes. But by the time you get to around here, there's a lot of differences between faces encoded here. And so what you can do is once you have these, you can take a new face that you want to do facial recognition on, project it onto maybe the first 20 or 40 eigenfaces, well, maybe more than that. And that gives you a point in a 40-dimensional space instead of a 40,000-dimensional space. And you use that to match your images against your database. Here is an example that kind of shows you how much information you lose when you do this projection. So on the left is an original photograph, albeit not a very good one, but whatever. If you take that and you project it onto the first 4 principal components, so project it onto a 4-dimensional subspace, you get this, which is not very recognizable. But if you have 50 components, then you could probably recognize your friend by that point. And instead of looking at 50,000 pixels, you can look at 50 principal components. So this technique has been elaborated on in many different ways. If you want to see an even cooler version of it using 3D models of faces instead of 2D models of faces, I have a link on the class webpage from today's lecture to a video by Blans and Vetter that was in a computer graphics proceeding somewhere that shows how to do a 3D version of eigenfaces, and it's a very cool, funny video, so I recommend it. And that's all for today, and on Wednesday I'll talk about clustering. Oh, and singular value decompositions briefly.